All right, thanks everyone for tuning in for this June edition of Friends of Lunar Volatiles. And so our presenter today is Kierra Wilk, who's joining us from beautiful Rhode Island. I assume it's beautiful. I've never actually been to Rhode Island. But Kierra is going to be talking to us about some of her dissertation work on studying variations in surface absorbed H2O on lunar soils and other minerals using spectroscopy. So just a reminder to everyone, if you're not speaking, please make sure your microphone's on mute. Videos can be on or off, up to you. And Kierra, do you have a preference for saving questions until the end, or do you prefer if people ask them in between? Either is fine.
They can ask as they go. If you put them in the chat, I probably won't see it. So
Mhm.
either we can get to them at the end or if somebody wants to speak for somebody else, that's fine.
Mhm.
And I'll
All
probably
right.
leave my video off just because I think the connection might be a little bit better, but
Mhm. Yeah,
sweet.
sounds good.
Okay.
All right, so take it away whenever you're ready.
Okay. Yeah, so hi everyone. Thank you for coming. Again, my name is Kierra Wilk. I'm a third, I guess going into my fourth year of my PhD at Brown University. And I'm excited to talk to you about some recent work that I've done looking at variations in surface water in relevance to a few lunar soils and then terrestrial analog minerals. So nominally anhydrous minerals, even though they are supposed to be nominally anhydrous, they do have mechanisms to sequester water or hydroxyl, or generally speaking, just hydration. So this could be through a variety of means, including internal hydration, where you might have fluid inclusions or structural defects, but you also could have external hydration as well, where you have water or hydroxyl bound to the outside of your mineral surface. So you could do this through physisorption, which involves really weak van der Waals attractions and happens at really low temperatures. Or you could have chemisorption, which involves stronger electronic interactions and will be stable at much higher temperatures. And so when we're thinking about the illuminated surfaces of the moon, it can get up to 120 degrees Celsius, as low as 100 and negative 130 degrees Celsius. And so when we're thinking about at least external water or hydration, we're generally thinking in the realm of chemisorption, which for water will start to desorb between 180 and 400 degrees Kelvin. So reflectance spectroscopy can detect hydration on planetary surfaces. And this is because water exhibits absorption features in the near infrared S regions. Here I have a conceptual spectrum of what water-related features might look like. And there's two different features I'll be talking about today, the 3 micron region and then the 6 micron region. So if we start with the 3 micron feature, the 3 micron feature is actually a broad and multi-component feature that is made up of 3 different absorption features. So this includes hydroxyl, that it can occur anywhere from 2.7 to almost 2.9 microns. Then there's the asymmetric and symmetric stretches of water near 2.9 microns. And then there's the first bending overtone of water at 3.1 microns. And you can imagine that it's quite difficult, and it is quite difficult to deconvolve the water versus hydroxyl signature, especially when you have both species present. But outside of the 3 micron region, we do have the fundamental bending mode of water at 6 microns, where we have no overlapping or coinciding hydroxyl features. And so if we do detect the fundamental bending mode, then we can confidently say that we have molecular water within our system. And so 3 independent spacecraft have detected the widespread presence of a 3 micron feature on the lunar surface that's consistent with hydroxyl and or molecular water on the lunar surface. This 3 micron feature has an observed latitudinal dependence, which we see on the plot on the left, where we have latitude on the x-axis and then water abundance on the y-axis. And as you get closer to the poles, that water abundance increases. And there's also this diurnal variability in the strength of the 3 micron feature as well, which is shown on the plot on the right, where we have our 3 micron feature shown in purple during the lunar morning, and it decreases in strength as the surface heats up as you approach lunar noon, which is shown in black. And then as you go back into the lunar evening and through the lunar night, back into lunar morning again, the 3 micron feature replenishes itself. So you know from these 3 micron observations that at least a portion of the hydration on the lunar surface is internal. So this is hydration that's in glasses, be it volcanic, agglutinitic, but they're going to be stable over these diurnal cycles. So they're not going to be thermally removed throughout the course of the lunar day. But there will be a portion that's external to our minerals, and that will be thermally controlled. And there's upwards of about 600 parts per million water in the polar regions. But despite all we know about the hydration on the surface through these 3 micron observations, it's really difficult to resolve the speciation of the hydration on the moon. And this is for a variety of reasons, in part because M cubed has near global coverage, but we have very limited, we're not able to resolve the full 3 micron feature. We're really only catching just the beginning of that 3 micron absorption feature. And then with the high resolution instrument infrared spectrometer, we get the full 3 micron feature, but we actually have quite limited observations, right? That's not what the mission intended to do. And then when you couple that with the fact that that 3 micron feature is not due just to hydroxyl or due just to water, it could be a combination of both. And then we don't have as many observations as we'd like of the full feature, on top of all the observations that we do have in great detail, aren't able to resolve the full feature. It just makes it very complicated, right, to resolve that speciation. Thankfully, though, right, the 3 micron feature isn't the only way that we can detect hydration with reflectance spectroscopy. And relatively recently, molecular water has been detected in the South Pole regions with the SOFIA telescope at 6 microns. And so this absorption feature at 6 microns has been interpreted to be the fundamental bending mode of water. And it's our first verification of H2O on the sunlit portions of the lunar surface. I should note that this is a very weak emission feature. I have a plot shown here of the 6 micron feature from SOFIA. It's been interpreted as internal hydration, potentially in glasses, but it's unclear if there is a superficial component to that 6 micron observation. And it's been estimated that there's an average of 250 parts per million of water in the South Pole from these 6 micron observations on their own. And so because the SOFIA telescope is detecting an absorption feature at 6 microns, and we believe it's water, the question then becomes, could coordinated 3 and 6 micron measurements resolve the speciation of hydration that we're seeing on the lunar surface? We have both the 3 micron and the 6 micron region. We can get an independent estimate of how much H2O there is. We can get a total water estimate from the 3 micron region, and from there we could figure out how much hydroxyl potentially that we have on the surface. So I, like many people, I'm really interested in what the speciation and abundance is of hydration on the surface, but particularly that diurnally varying component that I had mentioned earlier. And so through coordinated lab studies, I was hoping to answer 2 questions. I wanted to understand how small changes in water manifest at 3 microns. And then I also wanted to see if the loss and gain of superficial water was going to be observable in the 6 micron region, to test out whether coordinated observations truly would help us, especially targeted repeat observations, would help us figure out what is coming and going throughout the lunar day. So in this study, we acquired in situ reflectance measurements of terrestrial minerals and lunar soils. Our sample suite I have listed on the bottom, but we had anorthite, enstatite, olivine, a variety of particle sizes. And then we also had an Apollo 11 soil, a mature Mare soil, and then we had a mature highline soil from Apollo 16. On the right, I have just an image of what our setup looks like. So that's our Lincoln environmental stage. And that allows us to do these reflectance measurements while our samples are being heated. So we don't have to take anything in and out of the sample chambers between measurements. So we first measured these samples under ambient conditions, just to see baseline what they look like. We then purge the system with dry air. So it's been scrubbed for water. And then we gradually heat our samples up from around 25 degrees C upwards to 150 degrees Celsius for our lunar samples, so just hotter than the maximum temperatures they might have experienced on the moon. And then we went a little bit hotter for terrestrial minerals up to 200 degrees Celsius. And while we're heating them up, we're continually taking measurements of these samples to see how they're changing as we are assumably removing water or hydration from their surfaces. Once we reach our maximum temperature, we are cooling these samples back down to roughly 25 degrees Celsius, and then we're re-exposing them to the terrestrial atmosphere by just taking off the lid. And then we take another measurement of our sample to see what has happened to our samples. Okay, so results. We'll start with the 3 micron region first. So what we see is that the 3 micron feature, maybe perhaps no surprise to any of you, decreases in strength with increasing temperature. So here I have our olivine, enstatite, and anorthite spectra all have been continuum removed. The lighter green color is at ambient conditions, and then as you get to the progressively dark blue color, those spectra are at 200 degrees Celsius. We were interested in tracking a few things. So we wanted to see how the strength of this feature evolved, but we also wanted to see if the shape of this feature also notably changed with the loss of hydration. So if we start with olivine, we'll notice that the olivine 3 micron feature starts off relatively symmetric, and that's seen in the full width half max of this feature. But as we remove hydration, as we get hotter and hotter, that feature shifts from a relatively symmetric to asymmetric absorption. We see roughly a 60% decrease in the integrated band depth or the strength of the absorption feature. And there are notable changes towards shorter wavelengths in the band minimum position as well. For the enstatite, we do see, I should note, there is a sharp absorption feature near, I think it's 2.7-ish, 2.8, which is due to hydroxyl within the mineral. So we tend to not look at that when we're considering the band minimum. But we have an absorption feature that starts off relatively asymmetric and continues to be asymmetric throughout the heating series. We see roughly a 60% decrease in the strength of the integrated band depth through heating, and a band minimum position that stays roughly the same, but perhaps shifts slightly towards shorter wavelengths. A little bit harder to say due to that hydroxyl feature. And for anorthite, we start with an absorption feature that's symmetric, and it remains symmetric and actually kind of broadens slightly as we're increasing temperature and removing hydration. Yes, again, the band minimum shifts towards longer wavelengths, and we see about a 50% decrease in the integrated band depth of this feature. And then we can do the same sort of analysis with the 3 micron feature of the highland and the mare soil as well. It's a very similar story. As you heat up these samples, you're decreasing the strength of the 3 micron feature. The highland soil starts off relatively symmetric. It actually kind of looks no different than perhaps what we were seeing with the olivine sample or anorthite sample. And as you increase the temperature, you see a decrease by about 31% in that integrated band depth. And the band position stays roughly, the band minimum position stays roughly the same. And with the mare soil, we have a very asymmetric absorption feature. As we increase the temperature, we see a 33% decrease in the integrated band depth. And we have a band minimum that does stay roughly the same, but definitely is on the shorter side in terms of band minimum. Okay. So I mentioned not only did we heat these samples up, but I was interested to see what happened once we cooled these samples back down and re-exposed them to the terrestrial atmosphere. To see if what we were removing was a reversible process or was an irreversible process. And what we find is that re-exposure to the terrestrial atmosphere increases the strength of the 3 micron feature. So here for all of these samples in dark blue, we have the ambient spectrum. In the pink, we have our maximum heated spectrum. So for the terrestrial minerals, that's 200 degrees Celsius. And then for the Apollo samples, that's 150 degrees Celsius. And then in the dashed blue line, we have our re-exposed spectrum. So they had been exposed to the terrestrial atmosphere for about 15, 20 minutes. And when we took that spectrum. And so you can see that for pretty much all of these samples, the strength of that 3 micron feature does increase, but it does start to approach the ambient spectrum. I will note that for this heating that we're doing, we're not getting all that hot, and we do see that this process is reversible just by simply taking off the lid and letting the samples re-equilibrate for a few minutes. And combined with that low temperature regime that we're having, The changes in the 3 micron region are consistent with having the removal of chemisorpted H2O. So we're likely not removing hydroxyl because hydroxyl is a lot more stable than water is going to be. And you probably wouldn't start to seriously see the removal of hydroxyl until slightly higher temperatures. One thing that I do want to point out that is quite interesting and is at least was very noticeable to me was that we do see very different looking 3 micron features for our Apollo 16 and our Apollo 11 sample. So our Highland versus our Mare sample. And I just want to take a few minutes to think about why these sorts of samples or why these two samples look so different from one another. So the highland soil exhibits a much stronger 3 micron feature than our Mare soil. And it's not just the two samples that I chose. I went into Relab, downloaded all the spectra that I could that covered the 3 micron region. And I wanted to see what the integrated band depths were, regardless of the maturity of the samples. We see that the integrated band depth of the highland soils are roughly 2 times that of the Mare soils, which is shown on the plot here on the right. So we have kind of our spread of where we'd expect or where we do see integrated band depths for the 3 micron for our Mare and our highland. This spans a range of maturity. So it's not even, more mature soils have more water, or we're kind of having a sampling bias here. It doesn't matter. So why is this the case? One might speculate, okay, well, maybe there just are differences in internal water content or hydration content between the Mare and the highland samples. This wasn't something that I had looked at in my study. I didn't quantify any water abundances. A lot of people tend to ask that. So we don't actually know whether or not what the internal abundances are and whether that's contributing potentially, but I don't think at least in this case, maybe that's the only possible explanation. There could be differences in the terms of external water content. There is a study posted in all 2015 had looked at differences in the amount of external hydration on lunar soils. And they ultimately found that the differences between the highlands and Mare samples were because of soil maturity, or potentially because of soil maturity and composition. But I will note that in what I'm showing here on the plot on the right and includes a variety of soil maturities that we're seeing these differences. So even immature highland soils and immature Mare soils, we still tend to see a much stronger 3 micron feature. And then for the two samples that I had looked at, the Apollo samples have very similar maturity. So it's not likely a maturity difference, at least in my case, that is chalking up to the differences in the strength and shape of the 3 micron feature. But there is something potentially interesting when thinking about composition. So the composition of the highland and Mare soils are notably quite different, especially in the amount of opaques that are present. The ilmenite content is much higher in the Mare samples. And so it could be that because the Mare soils are so dark, you're actually the path length's much shorter and you're not interacting as much with the water. And so that could potentially be why the 3 micron feature for your highland samples, which are a lot brighter, have a much stronger 3 micron feature. But ultimately, I think it's very interesting. But if you wanted to truly figure out why these samples are so different, you would need water quantification coupled with in situ measurements to figure out if it's really difference in adsorbed water, the amount of opaque materials, or perhaps some combination of both, which might be likely. Okay. And so that kind of covers the 3 micron region. We see these very beautiful changes in the strength and the shape of the 3 micron feature that we're able to document quite well. But if we want to think about the 6 micron region, it's perhaps not as straightforward. And so I do want to start by saying that olivine, pyroxene, and anorthite all have mineralogy related absorption features in the 6 micron region. Chris Kremer has documented these absorption features quite well for pyroxenes and olivines at a variety of different chemistries. And many of these features, which are indicated by the arrows here on the figure on the left, are diagnostic of the composition of these minerals. And so if we're looking for water-related features for these sorts of nominally anhydrous minerals, it's very likely that these water absorptions may overlap or interact with these mineralogy-related features near 6 microns. And so rather than looking for a kind of discrete absorption feature, we might be looking for relative changes in this region to indicate the presence of water. Okay. Mhm. So what's actually happening at 6 microns? I would say not a lot, which is is quite surprising given how much change we're seeing in the 3 micron region. And we believe that we're removing this chemisorped water component. And so we should be able, in theory, to see it at 6 microns since the 6 micron feature is due to molecular water. Here I have on the right a figure showing a zoomed in region of the 6 micron region for all of our samples. Let's see, where should I start? So I look at this and I don't see that there's much change happening. There is a little bit of variation, especially with the enstatite sample. But while our normalization process is going to minimize any effects that we have, such as differences in albedos and spectral slopes, we are measuring these just under these like dry air conditions. So it's not like we're under vacuum. There's still going to be some variation that exists between measurements. And if you really wanted to convince yourself that, there truly wasn't any changes here that we could associate with water, we could look at the ratio of our hottest sample or hottest spectrum to the spectrum at 25 degrees Celsius. And so that's what I did. And for each of these, I don't know if you can see my cursor, but we have our spectra of the zoomed in region at 6 microns, and then we have our change in reflectance. The gray black box here indicates what the maximum variation is that we saw for mineralogy related features outside the 3 and 6 micron region. So things that shouldn't be changing, what that variation is. And so if we see variations that are greater than that maximum variation we're seeing elsewhere, then perhaps that might be significant. And then we would then go and look for changes in the 6 micron region that maybe we could attribute directly to water. But what you'll see is for all of these, if we look at our maximum variation, the variation that we're seeing falls within what we might expect. And there's nothing that stands out to me where it's like, okay, we for sure have a water related absorption here. And in many cases, especially for our Apollo samples, the maximum variation that we're seeing outside of the 6 micron region is very low. And then the variation that we are seeing within that 6 micron region is incredibly, incredibly low. And so again, we're not seeing any water related changes in the 6 micron region. Okay. So why is this the case? Ultimately, I wish I had a really nice, fancy answer for all of you, but I think something that deserves attention and could be a key player in all of this is thinking about the absorption coefficients. So the absorption coefficient for bulk liquid water at 3 microns is about 4.5 times greater than the absorption coefficient of water at 6 microns. So it could be potentially that we have enough water in our samples or on our samples to give rise to a 3 micron feature, but we don't have enough hydration or water to give rise to a discernible 6 micron feature. So the water's there, but we can only see it at the 3 micron wavelength region and not at 6 microns. And so what does this mean for SOFIA or just other future lunar remote sensing missions in general? I think it's perhaps unlikely or definitely calls into question the likelihood that we would see diurnal variations on the lunar surface due to adsorbed water in the 6 micron region, right? We can't detect the removal or gain of surface adsorbed water in the laboratory for these lunar analog samples and these lunar soils. And we have a lot of water in the terrestrial atmosphere, and there's considerably less in the lunar exosphere. So it might not be possible to actually observe diurnal variations at 6 microns. I agree that the 6 micron feature that they're seeing with Sophia is there, and it's most likely attributed to maybe internal or strongly bound water rather than that external component. But I think future work should really look at determining the detection limits of water at 6 microns for lunar relevant minerals, so things that we know, lunar or glass compositions where we know that there's water there, and we can detect a 6 micron feature to see or get a better sense of what that water quantification process might look like, and where it might be best applicable. So I did go kind of fast, but this gives us a lot of time, I think, to chat. So just to kind of summarize, we're documenting changes at 3 microns that are associated with the thermal removal of adsorbed water. We see differences between the Highland and Mare samples, which are consistent with global remote observations, that there may be differences in water content between the two. And these are, to first order context, great examples of what we might expect to see in the 3 micron region due to diurnal variations on the lunar soils, especially once we get data back from Lunar Trailblazer, which will be taking repeated targeted observations to look at specifically these changes in water content or the strength of the 3 micron feature. And we aren't, unfortunately, and very interestingly, seeing any water-related activity at 6 microns, despite having water present in our system. So I think I'll end it there, and I'm happy to take any questions and chat further. So thank you.
Awesome. Thanks, Kierra. That was super interesting. And I'm trying to wrap my head around it all. But yeah, we have plenty of time for questions. So what questions do folks have?
Oh, this is all super interesting. I wish Carl Hibbets were on. I'm sure he'd have good comments. Have you had a chance to talk to Casey about these results?
Yeah, so I've talked to
What does she think?
Casey. Yeah, so I think it's interesting because they're clearly seeing something at 6 microns with the Sophia data, but we're just not able to see similar changes or features in the laboratory data. So it could be potentially that maybe there's just a lot more water than we actually think. Or I don't know. It's kind of one of those things where it's like I'm seeing what I'm seeing and they're seeing what they're seeing. So how do we reconcile the two and what does that actually mean? Um, yeah, I think it's one of those things where we're both like we're trying to wrap our heads around it, and there's no good explanation, at least at the moment, as to why there's this difference in what they're seeing. But it could also be too that what they are seeing is an artificial component, and so perhaps maybe the bonding environment of the water or the hydration is just a lot more detectable in whatever form it is on the lunar surface than it is just on the surface for these minerals.
Yeah, I like the possibilities of the Mari samples are much darker, and the difference in the absorption coefficients between 3 and 6 that you noted. Might you do some rate of transfer modeling with the optical constants and just try to see how much
Mhm.
water produces a 3 micron band versus not producing a 6 micron band and so forth?
Yeah, I think that's definitely an interesting direction to go. And then also similarly, I think it would be great to get some synthesized samples as well, where we have just varying amounts of water and hydroxyl. We can measure them in the lab and then see what they look like, right? And kind of getting from a more, there's a modeling standpoint and then the physical standpoint, what do these samples actually look like? At what point do you no longer, even though you know you have water in the sample, can you no longer resolve it? And I think that's in my opinion, one of the next steps is seeing like what's the detectability limit of water in the 6 micron region, because that's also going to inform how we go about quantifying water with these remote sensing observations too. So
Yeah, if I can just build on that, and then I see David Goldstein had his hand raised in camera. So we'll go to him after this. But so thinking about detection limits, so I think Sophia, the rough estimates for what they were seeing was on the order of hundreds of ppm, if I'm remembering that right. And I know you didn't quantify how much water is present in your samples, but is there any, but you know, is there like just as a order of magnitude estimate, like do you have a sense of how much internal water there is in the samples you measured?
Yeah, I don't, and I don't feel comfortable like just throwing a number out there and then it
Right,
just
yeah,
kind of
yeah.
snowballs. I will say we had thought about trying to quantify from the 3 micron region like a total
Hmm.
water content estimate. Using SPAT is like a current or is usually how people
Hmm.
estimate water contents for their remote sensing observations. But the way that we measured them, it has a very small spot size, and so it, I ideally we'd want to have a much larger kind of field of view for our measurements, and so the modeling of that might get kind of weird. So
Hmm.
we ultimately didn't go that route, but I think that's also another direction where even just you take these samples and you measure them differently, you try to get a better sense of what these what the internal water content might be. Um, yeah.
Hmm. Cool. And David Goldstein.
I'm not an experimentalist, but uh, so the lunar samples in particular, they were little cups of powder.
Yeah, they were just they scooped them up, put them in the little vials, and yeah, they're like a particulate mixture.
So they were thousands of grains of stuff, right?
In the so yes, but in the way, and I didn't include this in the slide. We're using a microscope FTIR, so our spot size is 125 by 125 microns. So for the lunar samples, because the particles are much bigger, we're probably maybe getting 1 or 2 particles in the field of view, depending on the orientation of the particles within like our spot size.
And so when you thermally cycle these or expose them to lab air or whatever, do the particles move?
Yeah, so in some cases they can. So you have to be careful that they don't. So we have our little air inlet that's like constantly passing like this dry air through the system, and if the air is too strong, right, then you will move particles. So I had to make sure that it's not moving. But there is a camera, so you can see where like what's happening to your particle if anything does move. So they aren't moving. But if you're not careful, they can move, right? Because they're not all that large.
I guess what I was wondering is basically if you look at a particle slight on different side or something because of thermal cycling, the sample warmed and cooled or something, do you get a different measure? And I guess your answer is they're sufficiently stationary that that's not an issue.
Yeah, so in this case, they are sufficiently stationary, at least to our best knowledge, they're stationary. And we are able to observe them and see that they don't appear to be moving, at least within the context of the images. But I will say that depending on where you are, so like we were careful we have our little cup that's filled with our sample, and then it's being heated from the bottom. So depending on where you measure, if you measure in the center versus maybe more towards the edge of the sample dish, the temperature that it's experiencing might be slightly different. So it was really important to make sure that we were measuring in the same spot each time, to try to avoid any differences in the kind of what it's feeling thermally.
And then I guess sort of similarly, if you repeat the thermal cycling, do you get indistinguishable spectra?
For the most part, I mean, there's going to be some natural variation, right? Depending on like I measure this one particle, maybe it's slightly bigger than the other, so it might heat up a little bit differently. But we did these experiments multiple times, and the takeaway is still the same, right? You get roughly the same amount of change in the strength and the shape of the 3 micron feature. The spectrum might not line up exactly, right? But broadly speaking, you get the same results, and it's repeatable.
Okay, thanks.
Yeah.
All right, what other questions do we have? I had kind of a minor question that I just noted down when you were showing the re-exposed spectra. So they were re-exposed for, you said 15 to 20 minutes.
Yep.
And like, is that like if you measured them a couple of hours later, would you expect it to continue to grow at all? Like I guess I was trying to I was curious about the time scale for the band
Yeah.
to regrow.
Initially, yeah, so if you took a measurement later on, I think like you would expect that it would continue to grow, right? I had wanted to, when I was initially kind of designing the experiments, to cool them down, but then take continual observations. So I'd have almost like the opposite, right? Where I'm like, okay, it's slowly coming down. But once you take that lid off, when you're re-exposing it to the atmosphere, even within like a minute, that 3 micron feature is back, right? And so it wasn't very fruitful because it takes, about 45 seconds to make or to take one measurement. And by then you've already encountered most of your change. So, yeah, it would have been really cool to kind of see that stepwise progression. And I think that if you waited a lot longer, you would have a near full 3 micron feature.
Cool. What else? And feel free to either put something in the chat or raise a hand, or feel free to unmute as well.
Okay, I'll ask another one, if you don't mind.
Sure. Yeah, go for it.
Go for it.
There, besides minerals, are there more engineering materials for which you could check your measurement approach against, like 111 nickel or silicon, cleaved silicon or something where somebody else has the same answers?
Yeah, I mean, that's definitely a way you can go. I haven't really thought about that much, thinking about what else maybe that's a little bit more controlled might be helpful to look at, but I don't see why not. I will say that there have been, I'm blanking, and let's see, I'm trying to think of who. I know people who've been interested in like space weathering, and have done experimental space weathering and then looking to see changes in the strength of the 3 micron feature, and if there's anything happening at 6 micron feature or 6 micron region. They often don't see anything, and so maybe that means that, again, you're not forming any water during that process, which is totally possible. Or during that process, the amount of hydration that you are creating is not enough to show up at 6 microns. And I think the challenge that you would have is, especially if you're interested in external water, is getting enough water on the surface of your sample, especially if you need a lot of water. And that's something that we don't ultimately know. And I think we'd have to play around with, right, to figure out. Yeah.
Yeah, I guess some of our spectroscopists are on travel. So it's up to us to pretend we understand spectroscopy. So I can go on asking questions, but I want to give other folks the chance as well. But I'll in the meantime I'll go on asking questions. So Kierra, like I feel like you addressed like the questions you set out to answer really well. So, like how do the small changes manifest at 3 microns, and what do you see at 6 microns? And so one thing I was kind of trying to figure out what the takeaway should be is like, so what do you think the takeaway from this work should be, or is there a takeaway on the question of how do we untangle OH from H2O?
Yeah, I think the takeaway is that it's difficult. And I don't know, unfortunately, at the moment, if the 6 micron feature is going to be like the answer to all of our problems, especially in the lunar case or on these airless bodies where you maybe don't have a lot of water. which I think is quite fascinating. And there hasn't really been a lot of work yet to figure out, what does the system really tell us and what are the limitations of that system? So when you think about terrestrial minerals that have a lot of water, it works quite well, right? I've looked at a variety of hydrated minerals, clay minerals, where we're able to do like the exact same thing. And we can see these changes at 6 microns and we can see these changes at 3 microns. I think maybe even in the hydrated mineral case, perhaps a little bit more legwork could be done just to say, okay, like how much water do we have? How do all these features relate to each other? But yeah, I think I'm not confident, and I honestly don't know what fully the limitations are of using the 6 micron feature. So I think Tim has a question.
Yeah, Tim, go ahead.
So many weeks ago, when Parvati first brought your paper to our attention, and I buttonholed you immediately for a discussion with Casey Honeyball, Casey brought up the point, well, maybe you just don't have enough water, which of course seems kind of crazy for the moon, but is worth considering. So have you done any further experiments to see what happens if you intentionally dose the heck out of these things with water to see how much these features change?
Yeah, so when something that I did do was it's not included in this work here, but I let the samples sit in a humidity chamber. So it had air passing through that was like 99%, humidity. So it was humid.
Or like outside in Maryland in the summer.
Sure, yeah, it felt the water, right? It was wet, and I let them sit there overnight in the sample in the Lincoln stage. And by all means, they should have been as hydrated as they could be. I took those spectra, and they were no different than just the spectra at ambient conditions. And so, at least to my knowledge, externally, they're as hydrated as they could possibly be. And so I think it would be more or less a question of internally, could we add more water and then see what changes happen there? But externally, at least from my experiments, you can add as much, minus adding drops of water, which I did not try, and people have asked me. Yeah, we can't get these samples any more hydrated. Go. Yeah. And I think then you kind of potentially run into some other issues as well, right? Like, what are you measuring at that point, especially with the really small the sample size that we have?
And were they in the humidity chamber, were they at room temperature?
Yeah, so they're at room temperature with the humid air passing through.
Because of course the other distinction that is that the lunar regolith goes through that 80 Kelvin bath at night,
so
regardless of whatever moisture may be around.
Yeah, it'd be interesting to see at lower temperatures as well. Like if you have ice formation, right? Does that influence whether or not you're able to see anything? Or does that change your spectra? Which we know in theory, I think should change to some degree, but what it looks like, especially at 6 microns. Yeah.
Okay, thank you.
Yeah, thank you.
What else?
I have a question.
Yeah, go for it.
Great talk, Kierra. I was wondering if you can say anything about using the 6 micron feature, like volume correlated versus surface correlated internal water. Like let's say the water is in glass, then you might expect it to be present throughout the glass grain versus if it's in something else and it's due to solar wind implantation, it might be volume. It would be more surface correlated. So do you have any ideas on how you might be able to distinguish that?
Yeah, that's an interesting question. I think even more broadly too, not even just, internal versus internally, but like kind of very internal versus superficial, even just like internal versus superficial, right? Like what's the best way if you can't observe it? How would you distinguish that? I think, yeah, I'd have to think about that a little bit more, but I think you would definitely need a really good sample sweep with a variety of internal you kind of known profiles, right, of where your water is, and then you can maybe try to tease out what the signature, if the signatures look different. But I'm not entirely sure what the best way would be to go about that. Or like if I did this, I know that I would get this answer. Something to think about. And if you have any, I know that's not exactly what you do, the spectroscopy side, but if you have any thoughts, I'm happy to think about it more with you and what we could try to do to figure that out.
Sure. Yeah, I was thinking about, I think there's this figure in like the Dyer 2010 paper about like water in the solar system, and they kind of have this figure of like different grain sizes and surface or volume water, and they might have just done like optical constant work to see the sensitivity of that. So I was wondering if you could do something similar with the 6-micron feature.
Yeah, I think in that sense, you definitely could. I mean, smaller, when you're measuring bulk like a bulk sample, you have smaller particles, your volume to surface area ratio is going to change. And so you're definitely more likely to pick up that superficial component if there is one. But how you would go from kind of like superficial, but maybe still internally versus like internal, I'm not entirely sure.
And I had another question. Sorry if I missed it, but do you do separate grain size fractions for?
Yeah, so we did.
samples?
Yeah, we did. And the data that I showed here was our smallest grain size fraction, so less than 25 microns for all of these samples. So we did less than 25, 25 to 45 microns, and then 45 to 75. So even with our smallest particle sizes, with our strongest 3-micron features, we're still not able to see anything at 6 microns, which is also interesting as well, because maybe you'd expect for the larger particle sizes because we have a small spot size, we only have one particle, and the surface to volume ratio isn't high, you might not pick it up. But even with our smallest particle sizes, we still see the same thing.
Yeah, that's interesting because, like you said, the surface to volume ratio increases at the smaller particle sizes. So you'd have both more, I guess, maybe not more in terms of total volume of water, like adsorbed, but at least a stronger contribution. Like you have greater surface area in the smaller one, so you'd have more relative of the adsorbed phase as well as the solar wind implanted phase.
Mm-hmm. Yeah.
Interesting.
Yeah. Do we have more questions?
Okay, let me ask something.
Okay.
And
Sure.
just because I'm here anyway. So in our simulations of gas dynamics around the moon, some of the constants we don't know are whether a stuck water molecule on the surface is protected from solar UV dissociation, or to what extent it is. And another constant we don't really know is the thermal desorption timescale when we do molecular simulations. Can you shed light on either of those two constants, pun intended?
No, I wish I could since you asked. Yeah, no, I have no clue. And the other thing that's also interesting is like, and something I thought about was even though you're in a certain temperature regime, but like at what point are you going to start really desorbing? And it's kind of like a spectrum, right? So are you truly only going to be desorbing up until this temperature? What happens after that? How long does it take, right? Because clearly we're not also removing everything from our 3-micron feature. So there's certainly a hydroxyl component there, but is there still water hanging around, even though our sample is technically like too hot, right? Like how long does it take? So I wish I knew. Yeah.
Thanks.
Yeah.
Cool. All right. So we have 5 minutes left, and if folks have more questions for Kierra, please please feel free to ask those. But since so I was thinking of not meeting in July just because I know there's a bunch of conferences and it's summer and people are traveling. So I did want to ask before we get right to the top of the hour, but does anyone have any work that they're planning to present at the Exploration Science Forum next month, or any other news or anything you're excited about that anyone would like to share? I guess I can go first, but I am probably going to be at the Exploration Science Forum next month, and so I've been doing some work trying to model the gases that the Apollo 15 lander released when it took off. So exhaust from the Apollo 15 ascent module, and I've been trying to model that and compare it to measurements that were made from one of the deployed instruments. So that's how the actual comparison will turn out. I don't know yet, but hopefully I will by July, and I'm hoping to present that in some form. But does anyone else have anything else that they've been up to?
Oh, I was going to ask you, Parvati, which instrument was it, and did only Apollo 15 have that?
So this was so I'm trying to compare to the cold cathode gauge experiment results. So the CCGE, which was deployed on, I think, some of the other Apollos as well. And there are also measurements by some of the other instruments, so the suprothermal ion detector side. I've been focusing on the CCGE data because that's kind of the easiest to interpret and to do an apples to apples comparison against models too. But there have been sort of a number of detections of various anthropogenic sources by the Apollo instrument. So we picked this one because it's sort of clear data that's easy to understand. But there are other measurements and other instruments we could look at.
Yeah, 12, 14, and 15 all had the cold cathode ion gauge. I don't think 16 did, but I may be misremembering that. 17 replaced it with the mass spec, and I don't think 11 had the ion gauge either. Amazingly enough, this stuff is actually searchable on the NSSDCA these days because of the yeoman work of Dave Thompson at Goddard with trying to recover all of the Apollo ALSEP data sets to make them available. So those are out there. SIDE, I don't remember which mission SIDE was on. That would be useful. And then of course there was the mass spec, but I don't, it was far away from the vehicle. So I'd be interested in, well, SIDE was never operated in daylight. Not SIDE, sorry, LACE never operated in daylight. So you wouldn't be able to get anything. And that's one of the problems with the ion gauge also, that most of the time they just failed in daylight for reasons that one could have a lot of fine times arguing about over beer. So you have to find one where it was still actually working.
Yeah. Thanks, Tim. That's good info. And I was wondering who to thank for the information is sort of very accessible. And so yeah, it's good to know Dave Thompson was behind that. Great. Yep.
I said Thompson. That's a different guy. I got her. Dave Williams.
Dave Williams.
Okay. It's another Dave.
Awesome. Anyone else have anything they're presenting or been working on?
I wanted to plug, I'm not going to NESF, but I'm on the League XMAG Volatiles and Cold Curated Artemis Samples subpanel, which is our subpanel is chaired by Carl Hibbets. And so just a tiny update on what we've been doing. We have a draft of a report that is now with some reviewers to just take final looks at, and then that will be submitted to NASA at the end of the month. And Carl has an abstract on the whole process in the report for NESF, so stay tuned for for his presentation and then for the report, which should come out, I assume sometime this summer.
Awesome. Thanks, Alex. That's good info. Any other final news or questions for Kierra before we close out? All right. Well, if not, we are at the top of the hour. So thank you, Kierra, again for a great presentation and for answering all our questions. And yeah, Tarek says very interesting talk. And if Tarek says it, it must be true. And it was indeed a very interesting talk. All right.
Thank you for having me.
Yeah, thanks for dialing in, everyone. And so we will end it there for today, and we'll see each other virtually or in person sometime, somewhere. Right. Bye, all. Take care.